Hello and welcome to another episode of the Hidden Quantum Champions here on the Polaris School of Quantum channel. Today we are going to look at another one of those companies which you might have not really thought as a company that is active in the quantum technology space, and this is the company called Infineon. And here we are on their website. So this is the company website. Looking at it, it says Infineon technology powered by NVIDIA. If we look into the products, we find all types of different products from the electronic space. So we see ASICs, battery management ICs, microcontrollers, memory, sensor technology, wireless communication, and so on. There's also applications like aerospace and defense, automotive, home appliances, renewables, robotics, smart home and building solutions, design resources like simulation and modeling tools. So if you look at it, let's say a company that is from the top surface very much positioned in a space where they are working on classical electronics. Now, looking down here, we see that they are also looking in new types of electronics, like for example, cool GaN for the high mobility transistors, I guess, and there's other stuff down here. But I mean, there is not, let's say, prominently put anywhere that they are working in the quantum space. But if you actually look a little bit deeper, that's what you can find here. So there is some more information here. So we see on the right side, there's something which looks like a chip. It says V1.0 and Infineon. So quantum computers take us to new dimensions. Elementary particles that can be in several different locations simultaneously, entangled particles whose properties remain identical no matter how far away from another they are. The quantum world takes us to new dimensions. Here, many things are possible which would be unthinkable today in our macroscopic everyday world. As a leading semiconductor manufacturer, and I mean Infineon is definitely here in Europe one of the big names when it comes to semiconductor manufacturing. Infineon has expertise in the industrialization of technologies. Infineon is using this expertise to lead quantum computing from fundamental research into versatile application to make it an economic success and thus to make our society digitally more sovereign. Infineon is actively engaged in three roles. First of all, as a provider of components and solutions that make it possible to build competitive and scalable quantum computers. Second, as a user, advantageously applying quantum computers within the company and beyond. And then third, as an export authority and leading provider of crypto controllers, which will be able to withstand the attacks of future high-performance quantum computers aimed at the encryption algorithms used. Infineon is actively driving progress of post-quantum cryptography. So, what do we see here? Well, first of all, and I think that's the very interesting part, they are a component provider to quantum computers or to quantum technology, actually, because we also see that they are working on the cryptography side. So they provide, let's say, the silicon components. And I guess we will learn more about that later down in the page. Then secondly, they're also using it. So they are applying it probably for some types of simulations, probably in the future for optimization problems of layouts, whatever, of future generations of chips. And then thirdly, as an export authority, quantum crypto controllers, so on the cryptography side, post-quantum cryptography. So we have in the technology stack the computing side, but also the quantum communication and the cryptography side. So let's read further down. Practical approaches to the realization of quantum computers, a variety of different approaches to the production, manipulation, and reading out of qubits is currently being pursued. These approaches share in common the very great and highly specialized technical effort that they require. Typical basic conditions include, for example, temperatures close to absolute zero and high degrees of vacuum, both of which present substantial challenges in everyday applications. So that's referring to what we already know. The quantum systems need to be cooled down very much. Could be cooling, for example, of ions. We see ion traps here as a node, but could also be, if you look into superconducting systems, cooling down of the whole chip, right? And then, of course, vacuum is the other side. Usually those systems, they are in vacuum because if you go to super cold temperature, just literally every gas is freezing or becoming liquid. So you end up with a vacuum. And then, of course, on the other side, if you look at trapped ions, of course, you need to be able to separate your ions from everything else around them. So you also need a very high vacuum. So in order to rectify the error proneness of physical qubits, they can be combined to form ensembles and can thus be used in more complex calculations. However, depending on quality, anywhere from several dozens to 10,000 or even more physical qubits are needed to make a single error-corrected logical qubit. This is at the heart of the major challenge in developing the respective approaches. And that's also something that we've talked about before, right? We have these physical qubits that come with errors, that come with imperfection. And in order to, let's say, use them in these algorithms, we need to have this type of error correction, because otherwise, if errors start to accumulate, they're not localized to just a single bit, but they're spread basically across the whole chip because we want to entangle everything, right? So that makes it hard to remove those errors. That's why you need a lot of actual physical qubits to build a error-corrected logical qubit. And if you want to learn more about that, also check out the previous videos in this video series. The following chapter explains 3 strategies for making qubits: ion trap qubits, spin-based qubits, and superconducting qubits. All of them, I guess, with the help of what Infineon can offer. So, ion traps. In ion traps, lasers and microwaves put charged particles into precisely defined quantum mechanical states. These states last longer and are easier to control than in the case with the other qubit approaches. Comparatively speaking, the ion approach has already made great progress. At its Villach site, which is where the ion, where Infineon has a big production site. Infineon is working together, in particular with the University of Innsbruck, the Innsbruck startup AQT, and ETH Zurich. Here the focus is on the use of industrial manufacturing methods and scalable architectures to realize highly scaled quantum processors. A practical focus is on developing reliable high-performance quantum CCD implementation. CCD stands for charge-coupled device, in which shuttling operations move ions between specialized processor zones. Infineon technology demonstrates with sufficient storage capacity for 18 individual ions have already shown for the first time the parallel movement of 2 ion arrays. The function at temperatures of approximately 10 Kelvin, which means around minus 263 degrees Celsius, can be realized with comparatively little effort. So that's on the ion-based side, and I mean, we have already seen also some companies in the space of ion-based quantum computing, like one that we will see on the next slide. Then we also have the superconducting qubits here. So superconducting refers to the state in which electricity flows through a conductor with no resistance whatsoever. In the case of many superconducting materials, however, it is only possible at very low temperatures, close to absolute zero. Thanks to modern cryostats, which are essentially very powerful refrigerators, such temperatures can in the meantime be achieved with a reasonable amount of effort. Open bracket, still, in order to cool down, let's say, a very small little chip, which at the end is a cooling power in the, I guess, milliwatts range, you still need kilowatts of power on the compressors to actually create those cooling circles. And stay tuned in the Hidden Quantum Champion series, because we will also look at some of those companies in this space. I think we also have looked at one already previously to this video here. So if you wanna see which one it is, check out the playlist, and maybe somebody can drop it down in the comments below also. So back to the text, right? Reasonably low effort, right? Superconductors can be used to build circuits which behave quite similar to atoms. The states of these artificial atoms can be manipulated and read out electrically using microwaves. Superconducting qubits recently earned a certain reputation. They were the first technological platform on which the speed advantage of quantum computers could be demonstrated in an experiment based on a highly academic objective. At its Munich and Regensburg sites in particular, Infineon is working together with the Walter Meissner Institute of the Bavarian Academy of Sciences and Humanities and the Finnish startup IQM, which we've also already featured in this series earlier, amongst others, to use superconducting circuits for quantum computing. And then we also have the semiconductor-based spin qubits here. Silicon at the most widely used starter material in a Silicon at the most widely used starter material in semiconductor technologies is highly familiar and easy to manage. Together with germanium and other semiconductor structures can be created which catch individual electrons or their counterparts referred to as holes and use them as a qubit. Now, open bracket, this is actually the first qubits that I have seen in my researcher life. So more than 10 years ago, I was actually working in a lab that had those silicon-based qubits and did experiments with those. Close bracket. Infineon Dresden is focusing on spin qubits in this kind of silicon-germanium heterostructure. These qubits are robust and fast and provide excellent scaling potentials. The principle entails what is referred to as a quantum dot, in which appropriate fence electrodes are used to round up a two-dimensional sea of electrons until ultimately only one single electron is left. The spin of this individual electron is a natural quantum system in which the direction of spin represents the information carried by the qubit. In Infineon is working together primarily with RWTH Aachen University, the Leibniz Institute IHP Innovations for High Performance Microelectronics IHP and the Fraunhofer Institute for Photonic Microsystems IPMS. And then what else do we have here? So quantum computing, key technology of the future. What makes quantum computers so powerful? There's an explanation about the quantum computing basics. Again, where are the major challenges in the development of quantum computing and state of the art? Sites set on industrialization and application. Maybe let's quickly check this one out. From the very beginning, Infineon's contribution to developing quantum computers has supported the successful commercialization of the revolutionary technology. Infineon wants to help lead quantum computing from the realm of fundamental research into the world of application and economic success. This is why Infineon, as a founding member of the QUTAC, Quantum Technology and Application Consortium, is active in a consortium of leading German companies working to raise quantum computing to the level of wide-scale industrial application. Infineon places particular emphasis on industrial scalability of this technology. Outstanding scientists and engineers work at Infineon. Their expertise in chip design, materials, production, and hardware orientation software gives the company essential know-how capable of driving the development of quantum computing as decisive step forward. And again, here a quick note on this topic. I've also already pointed out other companies, not just Infineon, but also other companies here in Europe that have a lot of talent in their employee base that has a profound understanding of quantum technology. If I think of the people that I've been working with in the institute that I worked before, but also people that I know that have been working in the quantum technology space, some of them, they just moved to companies like Infineon and are now working there on the, let's say, classic electronic side of things. But of course, they do have an understanding of quantum technology, of quantum computing, quantum communication, whatever. And now as these companies like Infineon, but also others, I mentioned ASML, for example, before, as they are facing this new endeavors here, as they learn, as the quantum technology is developing, of course, they do have enough of an understanding to understand, okay, where in this game can we find a spot, where can we support, what could be our way in, and where can we add value. And I really like to see here that they actually have already their foot in the door with multiple of these technology stacks. So, findings in a new dimension: if quantum technology results in real, unique benefit for applications, the development of quantum computers could become a true success story. There are plenty of examples of tasks which are highly difficult or impossible to solve with classic computers. Here just a few: simulation of chemical reactions at the atomic molecular levels, targeted design of medications, development of innovative materials, for example, for lightweight design, catalysts and battery electrodes, close to real analysis of complex data, for example, for machine learning, optimization of complex logistics processes, and analysis of final processes and financial processes. And these are all points that we've heard about before. There's also something here on the security side of things, because we saw that before. They're also active in the space of the cryptography. Then there's related links here. It says new discovery, quantum computing, key technology for the 21st century. And there are more press links down here, or more latest news down here. And one of them is actually quite interesting, which is this one. Infineon teams up with Electron to deliver 3 generations of trapped ion quantum processor units. So this one I think is interesting, because here we have another one of those hidden champions, right, which is Electron with Q. So a company based off Siegen in Germany, which created a basically ion trapped quantum computer and also sold already this computer. And with that, we tap to the next one, to the next tab here, which I quickly wanted to hop into. I mean, there's dozens of more sites here on the Infineon website, and you can learn about all of this. I encourage you to check it out if you want to see what else they are contributing to. But just very quickly on the topic of trapped ion quantum computing. So Infineon ion traps accelerate the development of quantum computers. So Infineon has actively been working on creating ion traps for these companies. So Infineon ion traps enable scientists and startups to focus on their core tasks by providing a predictable, advanced, and reliable platform. We help in bringing a meaningful and powerful trapped ion computer, TIQC, to life to solve the optimization problems that have been waiting for decades to be solved. We help our academic partners to focus on what they do best, push the boundaries of science and research. We help our startup partners to focus on what they do best, find new ways, and integrate them into a successful and winning system. So predictable, repeatable, reliable, these are actually the important things, right? When you want to move from, let's say, a lab experiment towards something that becomes eventually a product that you can sell, you want to make sure that the processes that you are establishing, they are repeatable, they are reliable, so you can actually produce in the mass. And this is something where, like, also in the very beginning of computer technology, the early chip manufacturers, they were having problems with, and that actually made some of the, let's say, classical chip manufacturers at the very beginning either financially struggle or even go bankrupt. So if you look in the history of classical or of chip designers, there are some cases where people really were suffering to get predictable, repeatable, and reliable processes. So that now we see these big companies like, for example, Infineon, offering this to startups, I think is a very important step towards actually creating a business around this hardware. So what does it say? We know how to industrialize and combine novel materials and technologies. Infineon traps and trap designs are predictable, repeatable, and reliable. We are paving the road towards thousands of qubits by working with our partners on cryogenic control electronics and optics integration. To that end, we verify and characterize our ion trap modules in our in-house quantum laboratory. That's also very interesting. So they have their own quantum laboratory to do the testings of those units before they ship them. Custom tailored process lines in a high volume fab at our Villa fab. We are capable of working with wafer diameters from 6 to 12 inch, many different substrates, and a broad variety of process materials. Therefore, we can meet the particular needs of trapped ion quantum processors in terms of substrate materials, metal properties, and surface conditioning, supporting our academic partners and pushing the boundaries of science and research. What's next? So trapped ions at Infineon. What's next? So far, Infineon ion traps with a storage capacity of 18 ions have demonstrated parallel shuttling of 2 ion arrays in order to arrive at higher qubit counts of 100 or more. It's all about scaling and further improving stability. Physics has come a long way. With each step we take in scaling, we have to solve the myriad of engineering challenges that comes with it. We are working with our academic and startup partners on cryogenic control electronics and optics integration to pave the road towards thousands of qubits. So again, the important things: cryogenic control electronics. This is, for example, also interesting for superconducting qubits and for spin qubits, and optics integration, which is also interesting for the ion traps, right? And then we see here ion trap Gen 3, which is what we saw before, right? There was this press announcement with the socket trap modules. So there we have the module and cryogenic electronics that was mentioned before, like digital to analog converters, DUCs, at 10 Kelvin, at around 10 Kelvin. And again, this cryoelectronics part is important. I think I mentioned that before. If you look at the cryostats and at these chandeliers, like the different stages of the cryostat, the further you go from, let's say, the room temperature stage to the super low temperature, the lower the cooling power actually gets. So if you put in at the beginning 3.6 kilowatts of energy or whatever, you end up at the end with just, of power dissipation. At the end, you end up with like a cooling power in the milliwatts range, right? So with every stage, this goes down, or if you go from the low temperature side, with every stage it goes up, it has to go up. And that also means that it becomes more and more complex to get more of those cables down there, because one, of course, the chip is small, but also because you cannot draw an infinite amount of cables down there, because every cable, again, gives you a temperature coupling, and every temperature coupling again reduces the effective or increases the effective temperature that you can reach at the lowest level. That's why at some point you need to move cryogenics down, or you need to move electronics down to cryogenics level. And that's why this is playing such an important role, because otherwise at some point we just cannot get all the signals down and analyzed in the way that we are doing it right now, in a scalable way. Trapped ions intro, so then ion traps and quantum computing. Here's some information, I guess, on how it actually works. What is very cool is what we see here. So trapped ion shuttling, which is the idea of moving ions on this chip. So shuttling of ions provides the means of bring arbitrary combinations of qubits together for calculations. Therefore, it constitutes an important ingredient towards large-scale trapped ion quantum processors. Employing Infineon's ion trap chip, scientists at the University of Innsbruck have been the first to demonstrate parallel shuttling of 2 ion chains. And there's also, I guess, a video here. Usually I'm not playing the videos, but just to, I think, because you can actually see, yes, I think these are the actual ions that are moving here. So like single atoms that illuminate because I guess some laser shining on them. The video demonstrates a 2x2 array, ions being transported simultaneously. So yeah, you can actually see that the ions are being moved by these electromagnetic fields. And then you can move them close to have them interact with each other, take them apart to actually move them somewhere else and have them interact with other ones, or transport them to the readout area. So this is really cool. This is really exciting. And then again, we see here the news. Among them, there's this one about electron that we saw before. There's also Oxford Ionics joined forces to develop leading trapped ion quantum processors. Oxford Ionics is also a name that we've heard about before in this context, and of course in this context also IonQ. So you see there's a lot going on, and Infineon is basically very much part of this game and is very much central to this game. Let's quickly also take a look, because we always do that, also at the company itself. So Infineon. But as I said, you will not see, let's say, the standard quantum computing company here, right? So it says driving decarbonization and digitalization together. So that's the goals that they have. Decarbonization and digitization are at the heart of the mission of Infineon. The world must reduce carbon emissions and use energy more efficiently to secure quality of life for further generations. With our power system solutions, we are a key enabler in the move to harness renewable energy resources and deliver energy efficient solutions along the entire electrical energy chain. Together with our customers and partners, we make more out of less to actively shape a green future. And then digitalization. Digital transformation is changing the way we live, work, produce, and consume. With our smart IoT devices and system solutions, we link the real and the digital world and play a key role in unleashing the full potential of digitalization. Together with our customers and partners, we make the world smarter, so we can all look forward to a better tomorrow. And then here a little bit about the company. So a world leader in semiconductor technologies. They have 48K plus employees worldwide, so almost 60,000 people working for them at 71 R&D sites, 15 manufacturing locations, and an annual revenue of roughly 15 billion euros at this point in time. So it's a really, let's say, grown up large company in the semiconductor space. But as you can see, also very innovative, taking care of today's problems, but possibly also tomorrow's problems. And with that, I would like to close today's video. I hope you liked it. If so, please make sure to subscribe to this channel so you don't miss out on the next one. And see you until then. Bye bye.